Bismillahirrahmanirrahim. And the topic we are going to cover today is filtering, and the material presented in these slides is from the book Digital Image Processing, written by Gonzalez and Richard. It was written in the year 2011. So, as we know that image is not one dimension. Image is actually two dimensions. So we have a function for an image is f of xy, and for this f of xy we are we have first derivative of both directions. Like for x we have uh, a derivative fx, and for y we have derivative fy. So here it is called vector because it has two values of previously we were having a single value which was scalar, but as we have both values for the derivative with respect to x, and we have another derivative with respect to y, and we have two values, so it has direction. And it if it has direction, that it is a vector quantity, then this vector will be having some magnitude and a direction. So the gradient magnitude, for the calculation of gradient magnitude, we are squaring or f of x, and we are again squaring f of y, and then we are adding up the squares and taking the square root of it, and this will give us the magnitude. And as far as the direction is concerned, it is actually the uh, tan inverse of derivative of f of x upon derivative of f of y. So here comes how we apply a derivative upon an image. For example, we have derivative mask, which is with respect to x, it is 1/3 of -1 0 1 -1 0 1 -1 0 1. And similarly, we have another mask which is with respect to f of y. Like uh, we have we are having uh, 1.3 in the column wise 1 0 -1 for all three columns. So when we apply this mask and this derivative mask upon this image, for example, this was image 5 cross 5 image. So we are going to apply f of x on the uh, first 9 pixels. So when we are going to apply it upon first 9 pixels, we are going to multiply the first row with -1 and the last row with 1, and after that uh, we are getting 10 10 10, and after summing them up, we're going to get 30, and when we divide 30 by 3, we are going to have 10, this 10. So we replace this value with 10, and all we are going to get the matrix, this much matrix. We are going to move this window to those to the next pixel, and then next. For example, we are going to involve these 20 20 20 pixels next, and then next, and then so on, uh, for the entire image. And we are having first derivative upon this image x like this. As far as the uh, derivative with respect to y is concerned, and you have seen that it was a column wise mask. So you have this 10 and again this 10, because you are having same rows. So when you are going to make a difference of these points, then you are getting nothing but 0. So the image derivative with respect to y, you are having all zeros here. We have another term which is called correlation, and actually this is nothing but to multiply the value of x with the kernel h. So here we have uh, because we have a number of rows and number of columns, so we are going to multiply uh, it with the each row and with each column, and these for that purpose we have two summations, one for the x part and other is for y part. So we multiply uh, f k comma l to I plus k into j plus l. So actually we multiply it and we are having the result, and the operation we called it a correlation. So here is the function, here the function value, which is f, and these are the actual values which we are getting from an image, and this h denotes the kernel. So we do nothing but we multiply the corresponding values, like this f1 multiply f1, f2 multiply h2, f3 multiply h3, this thing, and then this, and then, and we are having f into h, which is actually called correlation by definition. And again we have a similar thing uh, which is called convolution. And again this is the same as we have seen earlier in the correlation, that we are going to multiply the function f with the kernel. But in this case the difference is here, that there it was I plus k comma j plus l, and here it is the difference. And why is it? Because we are flipping the kernel in the x direction, and we flip it, when we going to flip it in the x direction, we're going to have this one, and then we flip it again, and we flip it again, and this is called y flip, and we are having this final uh, kernel, and this final kernel is going to be multiplied with this functional values, which are actual values from the pixel, from the image, and when we multiply it we are going to have this thing f into h. But as we have flipped our kernel, so this is now called convolution, not correlation. But again you can see here, if the image if the kernel is distorted with some symmetric matrix, then this flipping will do nothing. So in this case, when the kernel is a symmetric one, so the correlation and convolution will be same by mathematics. Okay, this is an example of applying correlation. So it was actually the multiplication of the actual points upon the pixel, actual points on the image, and the mask catch. So we apply uh, this convolution upon an image by flipping this window from this point uh, to this point. So uh, for multiplication, you know the formula, but to take care of the coordinates, and which are these ones. Like if you are this is your window, this is your curved window at this position. If it at this position, then here the point x, this point x is actually the coordinate 0 0, and the pixel above it is having a coordinate 0 1, and below is 0 minus 1. So you multiply it h with x of y like this, and if you take care of these coordinates, then you will be having you will be solving it very easily and simply. And here is another terminology, mean, which you all know, that it is actually you add a bunch of items and you multiply it number of item and you are having a mean. And there is another term which is called weighted mean. Weighted means that you assign weight to every value uh, and then you divide it with the number of items. So it is called weighted mean. And this weighted mean, that you multiply every value uh, which is the part of the mean, you multiply it every value with some weight, and you then calculate the mean, and which is called weighted mean. So here we have an example of a Gaussian filter, like for example we have this function for Gaussian, and the expression for the Gaussian with respect to x is this. So actually we take minus of the square of x value, and we divide it uh, with the 2 into sigma square. This sigma is actually the uh, distribution, or this is actually the standard deviation, and so we are getting these values. And as far as the image is concerned, we are going to put and or apply the Gaussian filter not only in x but in the y directions also. So for the expression for xy is exponent e power minus x square plus y square whole divided by 2 sigma square, and again here sigma is the standard deviation. And for example for Gaussian, when we apply it on x, so you put the value 0 uh, in x. For 0 0 is this point, and at this point you are getting the much higher Gaussian value. So the maximum of this with this function we are getting 1. If we put 0 in the above expression, we are getting 1, and because 1 by 2 psi square on whole, we are getting e power 0 will be having 1. And if we put the value of x as 1, this expression gives us minus zero point 0.6, and if we put 2 over here, we are getting 0.13, and if we were putting 3 in this expression, we are getting 0.011. And this is as you know, the Gaussian is the symmetric function, we will be having same values for the negative side, and these values are calculated upon the standard deviation one. Gaussian is very important and interesting thing, and it has very interesting properties, like it is very natural model. It is a smooth function. Like a smooth function means that it has same values on the left side and same values on the right side, and it has infinite number of derivatives, and you can take infinite number of derivatives, as much derivatives as you require. And also the Fourier transform which is applied on Gaussian is also results in Gaussian. And convolution when we apply on Gaussian with itself, then again we are getting a Gaussian function. And Gaussian is named after the scientist Gauss, and who was very intelligent, and he was ahead of uh, his classmates. Like the first thing which belongs to him is the uh, summation of the numbers. Like he can add up uh, with all the numbers from 1 to 10, 1 to 30, 1 to 100, or even 1 to 1000 in the same amount of time, because it has developed a formula which we call today summation formula, like n by n minus 1 on all that. And there are important property of Gaussian is that there are some cells in our eye that actually performing Gaussian filtering in an human body. So these are very much interesting properties of Gaussian. So as you see earlier that filter is actually the modification and manipulation of neighborhood pixels. So we uh, modify the pixel on some function according to some function which are in the neighborhood of each other. For example, if we have this kernel and we manipulate it, we manipulate all the pixels and we replace the central value. This 11 will become 5.7 after applying the function f upon p. So this is actually the basic idea of filtering. So again, if we do linear filtering, the output is linear combination of the neighborhood pixels. Like this, if this is our image and this is our kernel, and we are going to apply the correlation, like we multiply image with kernel and we are getting the filter output, like this 10 will become uh, 5 after applying this kernel. So we have, in continuation to that, we have some more filtering examples. Like this was the actual image, and we apply this filter, and we are getting this image. Like it is identity. Like there is no change, and the same value of pixel which we are having in the main image or actual image will be replicated in the output of the image. So if we apply this filter, this kernel, and we multiply it with original image, then we are getting this image. Again, uh, what this kernel is doing here, this kernel like 111 and whole we divide it by 9, then actually we are averaging it, and we are averaging all the neighborhood values to the single to the common middle value. So what we are getting is the smoothen or we are getting smoothing. This is also called a smoothing filter. So we are having a smooth image. And if we uh, make our kernel bigger, then the sharpness will be completely gone. Like if we multiply or if we average the 25 pixels, then we are getting more smoothing, and it means that smoothing with very much smoothing or smoothing greater than some threshold point uh, is no longer desirable, because it is uh, making our image more blur. So after those examples of filtering, here comes Gaussian filtering. So as you saw earlier, that this Gaussian is actually have a bell-shaped curve, like uh, the value in the center is high, and the values in the left and right side of this filter are low. So when we are going to apply, when we apply this Gaussian filter upon the image, we're going to get uh, the output like this. Okay, here you can see that the difference between simple smoothing and smoothing with the Gaussian. So it is smoothing by averaging. You simple add up a bunch of pixels and then divide it by number of pixels. If it is 3 cross 3 kernel, then you are getting 9 values, and these 9 values will be get you are replacing these 9 values with the average of these 9 values. And if you take this average by uh, 5 into 5 kernel, then it means that you are making average of 25 values. And in case of Gaussian smoothing, it is actually the uh, different kind of averaging, like it was weighted average. Like Gaussian uses weights for its values because it has bell curve, and as you saw earlier that in the middle it was the weight was 1, and then the weight was next point it was zero point 0.6, and the third point was zero point 0.3, and it was the same in the both sides. So these weights actually preserve some sharpness in the image, so it gives you more accurate smoothing. So the Gaussian is giving you the more accurate smoothing. So here is another uh, notion which is called noise, Gaussian noise. So this uh, earlier you have seen that we were removing noise by Gaussian. Now here is the noise which has the property of Gaussian. So uh, this Gaussian noise, after averaging, you are getting this image, and after applying the Gaussian on this image, you are after Gaussian smoothing, you are going to get this image, and it is different from those the Gaussian which you have studied previously, because it has uh, the because the noise has the property of Gaussian. So because the noise has the property of Gaussian, so it is called Gaussian noise, because the noise is having those property of average and weighted average property. So it is called Gaussian noise. Okay, here we are going to discuss some MATLAB functions uh, which are very pretty useful when you uh, practically doing some examples on digital image processing. Like if the function conv is actually 1D convolution, like AB convolves vector a and b, and similarly conv2 actually it is two-dimensional convolution, like uh, you have these two uh, AB directions, and they perform the 2D convolution on these are actually the two matrices which are A and B. So in the first case 1D, this A, B were actually the vectors, and con2 actually performs two-dimensional convolution, and it takes two matrices and convolve it. So these are built-in function, and you can apply it while doing your practical exam. So there is another MATLAB function which is called filter, and it is again a two-dimensional digital filter, and it actually filters the data in the x direction with the two, and it uses filter actually uses 2D FIR filter in the which is applied on the matrix name B. So the matrix B filters the data in the x point in x direction, so by applying a 2D FIR filter. So as the result, Wise computing uses using 2D correlation, and it is same as the size of x. And similarly, this again this function which is filter to, it actually uses conv2 to do most of the work, which you have seen previous the function on the previous slide, which was conv2. So 2D correlation is related to 2D convolution, and by the 180-degree rotation in the filter matrix, and this all is taken care of by the matrix, and you do not have to worry and do it manually. So there is another MATLAB function which is gradient, and uh, which is called approximate gradient, like f of x and f of y. It was a gradient of the function gradient applied upon the function f. It actually returns the numerical gradient of the matrix uh, f into fx. which corresponds to the first derivative uh, uh, of the function with respect to x, and fy is actually first derivative with respect to y. So again there is another function which is called mean, and this mean is actually gives you the average or mean value, and for vectors this mean x is the mean value and average of all element in that x vector. So we have another function which is very important, which is called spatial, and it actually creates 2D filters. Spatial, very important MATLAB function which is actually creating 2D filters for you. And for example, this the filter which is actually the filter which is actually denoted by H is f special, and we have to put type over here. So this types the type of this filter in this f special is of these 6 types. It actually creating a two-dimensional filter for you, and the possible value for this type is one is average, that if you are creating an average filter. So, and the Gaussian, if you put Gaussian, then it will be create a Gaussian filter which will be a low pass filter. And Laplacian, and Laplacian means that Laplacian is actually the second derivative of x and the second derivative of y, and so this Laplacian filter can also be created by this function spatial. And then there is log, which is Laplacian of Gaussian, and it is used to detect edges. And then there is another type of this filter which is privet, and it is used to detect horizontal edges. And again we have a Sobel operator or Sobiel Gaussian for the detection of edges. And here we have an example that HF special Gaussian 7 1, it actually creating it is going to create a 7 cross 7 Gaussian filter with the variance or sigma 1. So the uh, reason of the 7 cross 7 Gaussian filter is that uh, if you are not having suppose you are having a small filter which is of 3 cross 3. So for the Gaussian you have a middle value which is 1, and a right value which was you have seen earlier, it was zero point 0.6 on the left and zero point 0.6 on the right. So you're not getting the big picture, you're not getting the full strength of the Gaussian with this, with the three actually values. So if you want to apply the whole strongness and whole impact of Gaussian, you have to get three values on the left and three values on the right, and so you can have the full impact of Gaussian. So here we take 7 cross 7 Gaussian filter, and with the variance 1. So uh, that's all for today. Thank you for listening.